Traversing trees is the idea of moving in between the nodes to achieve some goal. And since trees are naturally recursive, the whole tree structure resembles the same as part of the tree structure all the way down to the individual node. We can use recursive algorithms and in some cases non-recursive algorithms to traverse through the structure as it goes. So since we have this nice orderly structure to the organization, we can take advantage of that structure to be able to get to some answers or some ways of traversing things quite quickly. So, for example, the notion of the orderly storage, if we want to know what the greatest or the least value in a tree structure is, an ordered tree structure, a binary tree structure, there's a really simple formula to go do this. So if I want to know the least value, I just slide to the left. So left dot left dot left dot left until it's no longer null is always going to be the smallest value in the tree. If I want to know the biggest value in the tree, I just slide to the right. And so as long as I keep going down the right hand structure, I'm going to get to the biggest value. And that means in any subtree, then the smallest value is going to be the leftmost as well. The largest in the subtree is going to be to the right as well. And that plays well later on in some solutions. Now, using this knowledge, then, we can do some formulas around how do we order, for instance, the least to the greatest. So when I print out all the contents and I navigate through all the contents, I've got to do it in some order. So I can very easily do it from the least to the greatest. So the way I do that is if I know the lowest is the leftmost, well, if I print out the left subtree and then myself and then the right subtree and do that recursively, then I end up printing out from the least to the greatest. So let's think about this. So I print the left subtree recursively. So I start at the root. So print the left subtree of the root. Well, that's this one. My first step here is print the left subtree. Well, that's this one. My first step is print the left subtree. Well, that's this one. Left subtree, well, it's null. I don't print anything. And so then I print myself. I print the right subtree, that's nothing. And then I go back here. And so again, recursive, I'm coming back up. I've already printed the left subtree, so I print myself. And then print my right subtree. Again, nothing. So as you see, the leftmost subtree is 2, and then myself is 5, and then 11 is again myself, and then come down. Left is nothing. Myself is 14. Right, come back up here. 19 prints itself, nothing to its right. Then we come back up here. The whole left subtree of the tree has been drawn. 2, 5, 11, 14, 19. Then I print myself, 44. And then again, they do them in order on the rest of the way down. This really simple structure we can take advantage of to convert a tree structure into a flat structure like a list or a vector or an array, and they'll be in order. Just automatically, they'll be in order from least to greatest. Now, if I want to do it backwards, greatest to least, I just simply flip that structure. I print out my right tree first, and then I print out myself, and then I print out my left tree next. And so these two parallel algorithms have a very natural ordering to get to lowest to highest, highest to lowest. It's not the only ordering though, because we can talk about these three. We can talk about one other option inside of here. So there's this idea of traversal. Traversal is a strategy for walking through a tree. We just looked at the two in order options, the third bullet here, left me right or right me left. Well, I can also shift that around. So there's something called pre-order traversal, which is you evaluate your own self first, and then you do the left, then you do the right. Or the post-order traversal, which is you do your own self last. You go to the left, right, then me. And so the pre-order traversal is the idea of a bottom down dealing with a tree. I'm going to quote unquote visit is the magic word each node, starting with the top node, and then I'm going to do the left node and all of its subtrees, and then the right node and all of its subtree. The post being you do yourself last. So in this case, you go bottom left up and go from there. Now, the pre-order, post-order, generally speaking, we don't care about the order of the output at that point. We don't care if I do lowest to greatest or greatest to lowest. It's going to be kind of a jumble of the way those things are going to, excuse me, collect everything. But the post order is really useful, for instance, if you want to orderly delete a tree. So if I do myself last, I do all my left first and all my right, then myself last. For instance, I can take items off of a tree one at a time, and then I end up, you know, with only the base of the tree at the end. So the idea of algorithms to traverse trees has an important reason for two thoughts. Number one, you can start any behavior you want to do for the tree with pre-order, post-order, in order. Because if I'm doing recursive, I do me left right me, or left me right, or and I can combinations of left versus right inside of there. But those are the three kind of options of doing it in a recursive world, because I can only see those three things. If I want to do something slightly different, I can expand out and throw together, and we'll see an example of this in a little bit, looping plus some recursion to make that happen. But that that's other types of algorithms. Just the basic traversal idea is pre-order, post-order, in order. Now we use this concept of traversal as kind of a pattern approach. So I can actually, this whole idea of quote unquote visiting, I can use a traversal and then have a hole called visit. A hole being like an interface or an abstract class or something like that. So I could simply say traverse the tree, and for each node, make lowercase letters to capital letters. I could say traverse the tree, and for each node, delete any letter E's that are inside of there, or some sort of behavior, whatever you can imagine. I can use the traversal as a traverse the tree and do this thing, traverse the tree and do this other thing. And that's the idea of the patterns inside of here. There's different traversal patterns that we can either literally take as a pattern and we just code it multiple times using the same approach, or we can turn it into a framework where I pass code in and does it each way. Now, we're not going to do any of that here. It's a little bit beyond the scope of what we're doing at this point, but I wanted to play with this idea of traversal is a pattern that transcends any specific add, delete, remove, contains, search, whatever function. And it could be a part of all of them or implemented as a behavior on its own. So another thing I want to look at here, and a little helper I've added to the code for you, is how do I print a tree structure as it stands? And I can't do that at all in this sort of recursive behavior. And we'll explain why that is in the next video, where we're going to play with, I'm just basically going to walk you through some code that shows you a little bit about when the traversal patterns fall apart and I need to kind of do something a little differently.